In this video, I want to take a look at exam revision, the binomial expansion. So all we're looking at here is second year exam style questions for the binomial expansion. We do already have a video for the first year material, so if you're looking for the first year exam revision video, I'll leave a link to that in the description below. So like always, pause the video, have a look at the questions as they appear, and then double check that your solution matches what we get on the screen. Other than that though, I think that's everything that we need here to get started. So let's begin now with question 1. Starting off with question 1, then we've got this function f of x, which is equal to 1 over 1 plus 3x all squared. And for the first part here then, part A, we want to find the series expansion of f of x in ascending powers of x up to and including the term in x cubed. So for part A then, the first thing that I'm going to do here is just write down this function f of x. So f of x equals, I've got 1 all over 1 plus 3x all squared. And what I'm going to do here is I'm just going to rewrite this. So this is the same then as 1 plus 3x to the power of minus 2. Okay, just basic rules here of indices. And once I've got it in this form here then, we can now use the binomial expansion. Okay, so the result here for the binomial expansion, don't forget that is given in the formula book, but what I'll do is I'll just quickly jot down what we need here. So here we're going to use 1 plus x to the power of n. That result then is given as 1 plus n times x, so nx. Then have n times n minus 1. That is all over 2 factorial. Then we times it by x squared. And then finally, because we're only going up to the term in x cubed, I only need to go up to the term in x cubed here, obviously. So that's going to be n times n minus 1 times n minus 2. That's all over 3 factorial. And then we times it by x cubed. Okay. So that's the result that we need here then for part A. Now we do need to be slightly careful, or we need to do a quick check here. So we can only use this result if the number inside the bracket is 1, okay? If it's not 1, what we'd have to do is factor that number out. So for example, if this was 2 plus 3x, I'd need to factor the 2 out, okay? And that would ensure that this number here then would be 1. Now in this case here, it is simply 1, so we can go straight into using this result here. So we don't need to worry about anything like that, but it is always worth checking that is true, okay? So I don't think we're going to have enough room here to do it next to the actual question here. So I'm just going to drop underneath here. So I've got 1 plus 3x to the power of minus 2. 1 plus 3x to the power of minus 2. Like I said, we're now going to use this result here. So I've got 1 plus n times x. So n here is the power, so that's minus 2. Now just be slightly careful. When we've got x here, we don't times this by x in this case. We actually times it by whatever this is. So if this is 3x, we now times this by 3x. Okay. So for this question, when we're talking about x, that would be 3x in this case. Okay, so just be aware of that. So now we've got n times n minus 1. So n again is minus 2. So minus 2 times by minus 3. We divide that here by 2 factorial. So that's the same as 2 times 1. So that would be 2. And then we times it by x squared. So again, just remember x here is actually 3x. So it's just whatever this is. We times it by 3x all squared. And then finally for the term in x cubed here, what have we got then? I've got n times n minus 1 times n minus 2. So that's minus 2 times minus 3 times minus 4. That's all over 3 factorial. So that's 3 times 2 times 1. So that's going to be 6 there. Then we times that by x cubed. That's going to be 3x all cubed there. Okay. So what I want to do now is simplify each term here. Well, I can't do anything with the 1. So we'll leave that as it is. Minus 2 times 3x. That would be minus 6x there. Nice and straightforward. Now, for these next two terms here, I'll just save a bit of time. I'll just give you what you would get here if you were to simplify these correctly. Obviously, all you do here, for example, is -2 times -3, that's 6. Divide that by 2, you get 3. Times that by 9x squared there. Okay, so obviously, if you do that correctly, what you should get then is 27x squared. So plus 27x squared. And then finally, just doing the same here again. So just simplifying this. So -2 times -3 times -4. Divide that by 6 and then times that by 27x cubed here. And what you get then is minus 108x cubed there. Okay. And there we have it. So it's as simple as that, as straightforward as that. That is the solution to part A. So that's the series expansion of f of x in ascending powers of x up to and including the term in x cubed. So that's part A done. Now for part B, it says state the range of values of x for which this expansion is valid. So to determine the validity here, we refer to this here. Okay, so it's 1 plus 3x to the power of -2. We're not concerned about this number here. We're not concerned about the power. What we are concerned about is this here. Okay, what we refer to as x. So here, this expansion is valid. So the expansion is valid if mod of this here, so mod 3x, is less than 1. Okay. Now obviously we want the range of values of x, so I need to rearrange this here such that it's just mod x. So in that case, then what I'd get is mod x is less than 1/3 or a third there. Okay. And just know here, this is the same then as x being between -1/3 and 1/3. Okay. Whichever way you give it is fine, but either of these would be what you need there for part B. And then finally, we've got part C here. So we're going to run out of room. So all I'm going to do here is just quickly clear the screen for part C. So for part C then, it says, hence or otherwise, show that for small x, 1 plus x over 1 plus 3x all squared is approximately 1 minus 5x plus 21x squared minus 81x cubed. So to begin with here, I'm just going to start by writing down this fraction. I've got 1 plus x, and that's all over 1 plus 3x all squared. Okay. Now here we can rewrite this again, just like we did for part A. And notice it's actually pretty similar then to the original fraction here for this function. So I can rewrite this then as 1 plus x times by 1 plus 3x to the power of -2. Okay. So notice here 1 plus 3x to the power of -2, that was actually the series expansion then that we found in part A. If I think about this for a moment then, if I write down the series expansion here of 1 plus 3x to the power of -2, in other words, f of x here, and I times that by 1 plus x, that would be this approximation here for small x. Okay. So if I just write that down just so you can see what we're actually doing here. And don't forget, we do have the series expansion for 1 plus 3x to the power of -2. We found that in part A, so let me just write that down again, just because we have cleared the screen here, just so you can refer to that. So 1 plus 3x to the power of -2, that was equal then to 1 minus 6x plus 27x squared, and then minus 108x cubed. Okay. So here then what we've got, so therefore 1 plus x, we now times that by this here, so 1 plus 3x to the power of -2 is this here, and we expand it, we get 1 minus 6x plus 27x squared minus 108x cubed there. Okay. So here then, this expansion, it might look a little bit challenging potentially, but it's actually not too bad. So all I'm going to do here is take each term inside this first bracket here and times it by each term inside the second bracket. So for example, I take the 1 here, times it by each term inside the second bracket, and then we repeat that with the x here. And all we're going to do then to finish with is collect like terms. So if we do that underneath them, what do we have here? Well, 1 times 1 is 1. 1 times minus 6x there is minus 6x. Can't do anything with that. 1 times 27x squared, that would be positive 27x squared there. And then the final multiplication here for this 1 times minus 108x cubed, that would be minus 108x cubed. Okay. We now repeat this here with x. So x times 1 is x. X times minus 6x here, that would be minus 6x squared. And then finally, x times 27x squared, that would be 27x cubed. Now you might be thinking we've missed something here. We've forgot x times minus 108x cubed, but we don't need to do that because for small x, we don't go past any term in x cubed. Okay? So from here then, all we're going to do is collect like terms. If I collect like terms here, then what would we get? Well, we've got 1 here. There's no other, just single numbers there. So we can't do anything with that. So I just simply get 1. We've got minus 6x. We've got plus x there. I think that's everything there for powers of 1. So that would be minus 5x there. What you'll notice is we start working towards this then. I've got 27x squared minus 6x squared there. So that gives me 21x squared. So 21x squared. And then finally, I've got minus 108x cubed plus 27x cubed. Evaluate that and you get minus 81x cubed. Okay, so minus 81x cubed there. So what we're saying now then, so therefore, for small x, what we can see then is 1 plus x over 1 plus 3x all squared. That is approximately what we've just found here. Okay, notice we've got the exact same then as what was required. So that's 1 minus 5x plus 21x squared. And then minus 81x cubed there. Okay, as required. And there we have it. That gives us the solution there to question 1. So we just take a look now at one more question here. So I've got question 2. We've got this function f of x, which is equal to this algebraic fraction here. We're then told that f of x can be expressed in this form here. So in other words, this algebraic fraction can be split into partial fractions. And for the first part then, pretty standard stuff for us to find the values of a and b. So for part A then, all I need to do here then is take this algebraic fraction and split that into partial fractions. So we've got 2x plus 10. And that's all over x plus 1. We times that by 3 minus x there. So if we can split this here into partial fractions, what that means then is this here must be identical to a over x plus 1. So a over x plus 1 plus b over 3 minus x there. Okay. So the first thing that we're going to do here then is get this right hand side over a common denominator. So in that case then we get a times 3 minus x. We then have b times x plus 1. So b times x plus 1. That would all be over x plus 1 times 3 minus x there. Okay. Now, once we have it over a common denominator like this, what this means then is this numerator here must be identical to the original numerator here. So in that case then, a times 3 minus x plus b times x plus 1 That will be identical then to 2x plus 10. Okay. And what we're going to do here then is substitute values of x in so that we can eliminate one of the constants and solve for the remaining constant. So for example, if I let x equal 3 here, what would happen? Well, if x equals 3, this bracket here would be 0. 3 minus 3 is 0. A times 0 is 0. So what we've done then is eliminated A, but we can still go on to solve for B. Okay, so in that case then, we have B times 3 plus 1, so that's 4. So I get 4B is equal, well, 2 times 3 is 6, plus the 10, that gives me 16. So therefore, B is equal, so that's going to be 16 divided by 4, and we get B equals 4 there. Okay, nice and straightforward. So now we need to get the remaining value here, so that would be the value of A. So again, I'm going to do another substitution here. So if we let x equal, say, minus 1 here. So if x equals minus 1, well, what am I going to get then? This here would disappear because minus 1 plus 1 is 0. So B times 0, it disappears. So we get rid of that term there. And then here, I've got 3 minus minus 1. So just be very careful here. That would be 4a. I get 4a there. And that's going to be equal then. So 2 times minus 1, that's minus 2, plus 10, that gives me a. Therefore, if we want the value of a, I just divide both sides by 4. So a equals 2 there. Okay. And there we have it. So that's everything that we need there for part A. So that's the solution to part A. Now for part B, we're now looking for the series expansion of f of x in ascending powers of x up to and including the term in x squared. So because we're finding a series expansion here that involves partial fractions, there is quite a bit of work to this. So all I'm going to do to begin with is clear the screen, but do note these values here of a and b. So for part B then, like we said, this is going to be the series expansion here. Now this involves partial fractions. So like I said, there is quite a bit of work to this. So what we're looking for then is the series expansion of 2 over x plus 1 because a equals 2. So let's just note the values of a and b here. So a equals 2 and b equals 4 there. Okay. What we've got here then for f of x, let me just write that down again. So f of x equals, so we've got 2 over x plus 1. And then b is 4, so I've got 4 over 3 minus x there. Okay. So let's just rewrite f of x here. So writing this in index notation or index form, what I get then is 2 lots of x plus 1 to the power of minus 1. So just using the basic rules here of indices. I've got 2 lots of x plus 1 to the power of minus 1. And then for this one here, this is 4 lots of 3 minus x, again, to the power of minus 1. So plus 4 times 3 minus x there to the power of minus 1. What I need to do now is use the binomial expansion 2 times. So I'm going to use it here on x plus 1 to the power of minus 1. I'm going to use it again here then on 3 minus x to the power of minus 1. And all I do then is I add those together. Obviously, what I need to do is multiply this expansion here by 2 and this expansion here by 4. But once I've done that, I can find the full series expansion by finding the sum then of those 2 individual expansions. So let's start by finding the expansion here of x plus 1 to the power of minus 1. Obviously, I need to times that through by 2 as well. So let's just write down the result then for the binomial expansion before we do anything else. So for the binomial expansion here, we're going to use 1 plus x to the power of m. And we're only going up to the term in x squared, so that saves us a little bit of kind of work here. So the result here is 1 plus n times x, so nx. And then for my term in x squared, I've got n times m minus 1. Divide that by 2 factorial, then we times it by x squared. Okay, so this is the result that we're using here. Like I said, though, for the previous question, it is given in the form of the book, so you don't have to worry about memorizing this result. So, for 2 lots of x plus 1 to the power of minus 1, that's 2 lots of the expansion here of x plus 1 to the power of minus 1. Now, the first thing that I always need to check here is that this number on its own is 1, because we can only use this result then if this number is 1. Okay, so this is positive 1. We can go straight into using this result then. So here I'm going to get 2 lots. I get 1. We then have n times x. So n here is minus 1. I've got minus 1 times by x, which is just simply x. So minus 1 times x there, nice and straightforward. And then for the term in x squared, I've got n times n minus 1. So that's minus 1 times minus 2. We divide that here by 2 factorial, so that's 2 times 1, which is 2. And then we times that by x squared, so x here is just simply x, so it is just going to be x squared as well. Okay. So close those brackets. So what I need to do now is simplify everything inside the square brackets. So we've got 2 lots. I've got 1. Minus 1 times x is minus x there. And then minus 1 times minus 2 is positive 2. Divide that by 2, I get 1. Times that by x squared, and we simply get plus x squared there. Okay. So now, if we times through by 2 here, 2 times 1 is 2. 2 times minus x is minus 2x. And then finally, 2 times positive x squared, I get plus 2x squared. Okay. And there we have it. So that's the first expansion found there. So hopefully nice and straightforward for the first one. So now for the second one here, I maybe should have color coordinated this, so it might have been a little bit easier to see. Let me just do that here, just so you can kind of see what I've got. So this one here, what color have we got here? Let's do it in orange. So this expansion here, this is this part here. Okay. And then for the next part, let's do that in blue. That will be this expansion here. Okay, so I'll go back to the original pen color, but again, I'll highlight which part that actually is. So now, for 4 lots of 3 minus x to the power minus 1, this is a little bit tricky, and you'll see why in a second. So let me just write it down to begin with. Got 4 lots of 3 minus x here to the power of minus 1. Okay. So the question here is then, why is this a little bit trickier? So just take a look at this for a moment and see if you can identify why we can't just use this result here. And hopefully what you recognize then is because this number here isn't 1, okay, it's 3. We can't use this result here. Remember, we can only use this result then if this number is 1. So the way that we deal with this here is we factor this number out. What I'm going to do then is I'm going to factor 3 out from this full bracket here. What I get then is 4 lots of 3 here. And then we times that by 1. Obviously, if I factor the 3 out here from the minus x, that's minus x over 3. So minus x over 3. And don't forget here, so that's the power of minus 1, but don't forget, once you factor this number out here, so in this case 3, you also need to raise that to the power of n, where in this case n equals minus 1. So that's 3 to the power of minus 1. In other words, 1 over 3. So 4 times 1 over 3, that's 4 over 3. So what I've actually got here then is 4 over 3 times the expansion here then of 1 minus x over 3 to the power of minus 1. So 1 minus x over 3 to the power of minus 1 there. Okay. So what we've done there is basically got everything basically in the correct format. So now what we can do is we can now use this result here. Okay, so you have to be very careful for that here to begin with. So now, if we use this result here, I've got 4 over 3. So we times that then by, well, I've got 1. We then have n times x. So n here again is minus 1. So plus minus 1. But now be careful here for x. So in this case here, it isn't x, it's actually minus x over 3. I've got minus 1 times minus x over 3. What else do we have here? Well, that's the term in x. We now have the term in x squared. So I've got n times n minus 1. We divide that by 2 factorial. So n here is minus 1. I've got minus 1 times minus 2. That's all over 2 factorial, which is 2. And then we times this here by x squared. So x again, it isn't just x, it's minus x over 3. So we times it by minus x over 3 all squared. So minus x over 3 all squared. Okay. So what I need to do then is simplify everything inside the square bracket here. So I've got 4 over 3. And then times that by, so what have I got? Well, I've got 1. Can't do anything with that. Minus 1 times minus x over 3. That would give me positive x over 3. So I get plus x over 3. And then here, what have I got? Well, minus 1 times minus 2 is positive 2. Divide that by 2, I get 1. I've got 1 times minus x over 3 all squared. So that would be x squared over 9. Okay, so I times x squared over 9 by 1. I would simply get x squared over 9. So plus x squared over 9 there. Okay. So now all that remains to do here is to multiply through by this term here on the outside. There's 4 over 3. So if we do that then, 4 over 3 times 1, I get 4 over 3 there. I've then got 4 over 3 times x over 3. So that would give me 4x over 9 plus 4x over 9. And then finally, 4 over 3 times x squared over 9. That would give me 4x squared. So plus 4x squared over 27 there. Okay. So what that represents then, what that represents here is the expansion then of 4 lots of 3 minus x to the power minus 1. So this here, that's this expansion. Okay, like you see, there's a little bit more work for that second expansion there. But what we've got here then is everything that we need then for this series expansion of f of x. So in that case then, so if I do it underneath, therefore, the series expansion then would be 2 over x plus 1. I've got 2 over x plus 1 plus, so I've got 4 over 3 minus x there. And like we said then, that would now be the sum of the individual expansions. So what I'll do again is I'll use the same colours here. So the orange part is 2 minus 2x plus 2x squared. That's this bit here. I get 2 minus 2x plus 2x squared. Okay. So that's for this bit here. Do a bit of orange underneath just so you can see what that links to. For the blue part then, that's this fraction here, 4 over 3 minus x. So the series expansion for that then is 4 over 3. So I've got plus 4 over 3 plus 4x over 9. And then finally 4x squared over 27. Okay. So to finish with then, all we need to do here is evaluate this. So essentially just collecting like terms. I've got 2 plus 4 over 3. So all you need to do is just use your calculator. You don't need to do this by hand. So it'll give me 10 over 3. So I get 10 over 3 there. I've got minus 2x plus 4x over 9. Again, just use your calculator here. This gives me minus 14x over 9. So minus 14x over 9 or minus 14 over 9x, whichever you prefer. They are the same, so that's fine. And then 2x squared plus 4x squared over 27. Again, just use your calculator here. And what you should get if you do this correctly is 58x squared over 27. Okay. And there we have it. So that's the series expansion there of f of x in ascending powers of x up to and including the term in x squared. So that's part B done. And then finally for part C here, it says state the range of values of x for which the expansion is valid. So we don't have a lot of room here. Let's see if we can just about fit this in. So I kind of split this off a little bit here. Okay, let's do part C down here. I think we should just about have enough room. So for part C then, to find the range of values of x for which this expansion is valid, what I need to do now, because we're using partial fractions, is consider the validity then for each individual expansion. So for two lots of x plus 1 to the power of minus 1, so let's write these down individually then. Again, I'll use the same colours here just so you can see what it links to. So 2 over x plus 1. This is valid if mod x is less than 1. Okay, so this is valid. This is valid if mod x is strictly less than 1. Okay, so that's this first expansion here. So for the blue one then, let's consider that validity. So 4 over 3 minus x here, that is valid if mod x over 3 is less than 1. Okay, obviously we're concerned about the range of values of x here, so if I rearrange that then, that is mod x is strictly less than 3. Okay, so now if I think about this on a number line then, let's go back to a different colour here. If I think about this on a number line then, let's say this here is minus 3 and this here is positive 3. Okay, in the middle, let's say that's there, we'll have 0. So what I've got then is this expansion, which is valid if mod x is less than 1. So in other words, between minus 1 and 1. So if I say that's minus 1 here, minus 2. It's not perfect, but you get the idea. 1 and 2. Okay, so this one, let's do it in the same colour then, so I can be consistent. That's valid between minus 1 and 1. Okay, that should be a clear circle. Let me just redo that so it's correct here. So I don't want it to be misleading. Okay, so between minus 1 and 1. However, for the blue one then, that is valid between, so it's valid between minus 3 and positive 3. Okay. However, if we think about this for a moment, the full expansion then can only be valid when x is between minus 1 and 1. Obviously, it can't be minus 2 because we would fall outside the range of acceptable values then for this expansion here. So if you think about it, it's always a smaller range when you have a number of ranges like this. Okay, so therefore then, let's just clear all that and we'll answer part C then, just in one line. So therefore, for part C then, the expansion is valid when mod x is strictly less than 1. Again, you could represent that as x being between minus 1 and 1. Either way, that would be fine there. Okay. And there we have it. So that gives us the solution to the very last question. Question 2. Like you can see, we've only done 2 questions here, but these questions do go on for quite a while. I know towards the end it gets a little bit trickier to kind of stay on track, but hopefully you find this video helpful. And like I said, that's the solution to the very last question, and that brings the end of this video on exam revision for the binomial expansion.